Hello everybody, my name is Arturo and I will be presenting to you NOMAD, a natural occluded multi-scale aerial dataset for emergency response scenarios. A work done in collaboration with Dr. Walter Scheirer and Dr. Cleland-Huang from the Computer Science and Engineering Department of the University of Notre Dame, USA. So let's get started. First of all, I believe we need to answer the question, why NOMAD? Why the need for NOMAD? Well, emergency response scenarios such as search and rescue missions are situations in which first responders are compelled to act fast to save lives. Improvements in technology have allowed them to transition from requiring a helicopter to obtain aerial views to fast and safe deployment of small unmanned aerial systems, sUAS, such as drones, which is how I will be referring to during the presentation. So from small to big departments, first responders are experimenting an increasing reliance on drones for emergency response scenarios, not only in the US but around the world. Nevertheless, deploying a drone in the air is not a guarantee of success. And when we are working on a critical task like emergency response, improvement becomes a must. Therefore, when working towards higher levels of collaboration between first responders and drones, the integration of computer vision capabilities into them becomes a key factor in mission success. But to achieve this integration, we must face several challenges prone to surround emergency response scenarios, such as real variance of facing natural imagery, going from is the victim over water or over ground, is it winter or summer, what's the scale, the resolution of our target, at what distance are we flying, and one of the toughest challenges, occlusion. In emergency response scenarios, we can never be certain that the person's body we're trying to rescue is always going to be completely visible. In fact, more often it's not. Occlusion is a critical and tough component that computer vision and human vision have to face in emergency response scenarios. And we have to face all these when even shifting from ground to aerial detection is already a challenge for our current computer vision models. Work from the community to solve this shifting problem has been great actually, creating several helpful aerial datasets contributing towards solving the natural real variance and multi-scale challenges in the way. However, none of them has specifically addressed the issue of occlusion, a critical component in emergency response scenarios. With that in mind, we built NOMAD, a natural occluded multi-scale aerial dataset for emergency response scenarios. Now, building NOMAD involves several stages, from data collection to data annotation, each stage providing additional deliverables. Following our IRB-approved protocol, all participants are at least 18 years old, with the recruitment process done with the goal of achieving a diverse population. Additionally, filming locations were used with prior approval from owners and all responsible agencies. During the filming session of the data collection, each actor was given instructions of hiding, laying, and walking around a uniquely assigned obstacle. All actors were asked to repeat the routine 5 times, with the drone set at 5 progressively distant locations of 10, 30, 50, 70, and 90 meters. Finally, we also collected a ground 360-degree view of the actor and true negative of each location. Following our IRB protocol, non-participants were removed either by trimming or blacking out specific pixels. Further, we perform a keyframe selection from each routine video, as manually labeling all frames would be unfeasible. Some rules were used during the selection. The selected frames must track the actor across their entire routine. That means that the starting and ending frames of a trajectory were selected as keyframes. But also, each change in direction of the actor's trajectory generated new keyframes. And finally, the set of keyframes must include different poses. Additionally, activity labels were assigned to keyframes and custom sampling at occluded frames was performed to obtain views with different levels of occlusion. And this takes us to the data annotation process, where all 42,825 selected frames were sent to label box, to add bounding boxes and visibility labels to all images. And finally, we have reached the visibility label, our metric for occlusion. First, percentages were assigned to parts of the human body. Then, for each bounding box, we added the percentages of the human body visible at the current frame. And then we assigned the sum to one of the 10 predefined ranges of visibility with upper bounds of 10 to 100. That is, for example, if the addition was 15, this was set to the range of 11 to 20, named as 20. During this calculation, shadows were not considered to be part of the human body, and under normal circumstances, the actor's own clothing is not treated as a source of occlusion. So what's NOMAD? What is NOMAD? NOMAD consists of 100 different actors, 42,825 manually annotated frames, 500 routine videos, 5 distances per actor, 100 reference video, 500 true negative videos, 5.4K video quality, environmental and demographic metadata, including outfit description for every actor, a visibility label for every bounding box annotation, and activity labels for every routine video. NOMAD is built to tackle the natural, occluded, and multi-scale challenges of emergency response scenarios by providing location diversity, cross-seasonal imagery, demographic diversity, 10 levels of occlusion, and 5 different scales plus a reference ground view of every actor. The variety of locations provides coverage of natural and man-made environments and is aimed at training computer vision models for effectively supporting a wide range of emergency response scenarios. The gender distribution shows a 50-50 male-female distribution, and although age distribution shows that the majority of the population was younger than 30 years old, actors across the range of 30 to 78 years old are still present. When compared to the USA race distribution, NOMAD presents a better distribution with the goal of avoiding possible biases. So, to exemplify NOMAD's use as a benchmark for occlusion, we tested 3 state-of-the-art computer vision models on NOMAD against different distances and levels of occlusion. For evaluation purposes, 10 folds of 10 actors each were randomly created with a constant seed for reproducibility across models. From each fold, 50 tests were performed, 1 per each distance visibility pair, with the results of these 50 tests being averaged across the 10 folds. This gave us the following results. First of all, we need to know that occlusion increases as the level of visibility decreases on the charts. Therefore, on all 3 models tested, MAP scores fall drastically as we increase in distance and occlusion. The higher performance of the model at the closest distance is expected as the data resembles ground view from COCO training data, which was the training data used for these models. Nevertheless, MAP scores fall significantly as we increase in occlusion even for the closest distance, calling for improvement and robustness of models against occlusion in aerial views. So future work exploiting NOMAD is planned on detection under occlusion by exploiting human psychophysical metrics and temporal information, person re-identification by leveraging software architectures that support hybrid onboard and off-board solutions and integrate the human into the loop, and finally, real-world deployment. Our end goal is to deploy and evaluate occlusion-ready computer vision models on physical drones. To close this presentation, the structure and characteristics of NOMAD offer many opportunities for improvements in aerial human detection, recognition, and tracking. In conclusion, as indicated by the results of our baseline evaluation, occlusion represents a non-trivial challenge that remains to be tackled. NOMAD's characteristics of natural, occluded, multi-scale aerial views provide a new benchmark dataset for tackling this challenge, and can serve as the next step for improving the accuracy of aerial search and detection for emergency response. Thank you very much. I hope we have answered most of your questions. If not, please feel free to access our paper. And if the only remaining question is, where can I find NOMAD? Please feel free to visit our GitHub link. Thank you.